It is now my pleasure to invite our chief guest, Professor Ajay Kumar Sood, to address the gathering. Professor Sood's address will offer valuable insights into the intersection of science, technology, and national development. Please, sir. Yeah.
First of all, heartiest congratulations to the entire fraternity of Ministry of Earth Sciences, Dr. Ravi Chandran, Mr. Vishwajit Sahai, Mr. Senthil Pandian, former secretaries of this department, and all of you who are here online as well as in the hall. It's a great moment to look at what has been achieved in the last almost 25 years, silver jubilee of your parent department from which you originated. Let's not forget the mother of all this. And it has really made a huge journey. One really wonders what was happening 25 years before, because this ministry, as was so eloquently pointed out by Mr. Sahai and Ravi, that it is looking at almost all aspects of human existence. Whatever we need to survive and what we need to leave behind for future generations. Both aspects are so very well handled by this ministry that your canvas is really huge to look at. It's sometimes really overwhelming to see what all this ministry is doing and what all it has the capability and capacity to build in coming years. So I will not be actually qualified to say anything on what already has been added by Ravi in the last few minutes. But I just thought, I just took note of what MOES has been doing. All the five verticals which was pointed out, be it in weather, climate, and hydromet services, ocean services, seismological, polar science, and whatnot. In all of them, you have made tremendous achievement. You have contributed to our nation building, and that is why the expectations are increasing of the nation from this ministry, because it connects all aspects of life, including the strategic sector. So I thought I'll just share a few minutes with you on how I look at it. And the reason for the slides actually is Ravi's letter. The reason is when he called me to come for the foundation day, I agreed because you never say no to a friend. But only when I started looking at the letter this early this week, I realized that he is so generous. He has allotted 25 minutes for this address. And that worried me because I have seen in my last 2 years as a professional hazard to inaugurate things and give Foundation Day inauguration. You can hardly talk for 5-7 minutes without the slides, and then it is repetitive. And everything that has to be said has already been said by Vishwajit ji and Ravi ji. So there is nothing I can add. So I thought, let me say a little bit how my present responsibilities connect to what you are doing, and a suggestion which probably has not crossed your mind, but it could be futuristic to look at. So that takes me to where we are today. So in my office, in Principal Scientific Advisors establishment, we have two instruments to work with. One is called Prime Minister Science, Technology and Innovation Advisory Council. And we have few members and permanent invitees where Secretary Ministry of Earth Sciences has been participating in the last 5 years. And another one is to look at Empowered Technology Group, which is really looking at procurement and induction of technologies above a certain value and R&D in technologies that require large outlays in resources, both financial and human. So these are the two arms. And in the PM strike, many discussions, many deliberations have happened. And I'm happy to say that in the last 5 years, all 11 missions have been nucleated in PM strike, which have been taken up by different ministries, and they are at various stages of implementation. I have written few of them just to connect with today's function. And this one is the Deep Ocean Mission. This was discussed in October 2018. I was a member of PM Strike at that time, and Vijay Raghavan was the PSA. There was absolutely no doubt that this has to be done in a mission mode, and I'm glad to see that this mission is going ahead in the last 1.5, 2 years, or maybe 3 years now, and it has a lot of deliverables under this. Then we have, for example, AI mission, which was discussed again earlier, but fructified in the last 1 year. Then we have National Mission on Quantum Technologies. Again, a very futuristic mission. I'll say a few things on this, how it can connect to Ministry of Earth Sciences. And One Health Mission, again, a very important mission, which was again alluded to earlier by Ravi, that how we can look at human health, animal health, and environment together. And the pandemic has taught us that all these three verticals are not isolated. They interact with each other and influence each other. So this One Health Mission has 11 ministries participating in it, steered by ICMR. And here the idea is to really bridge the gaps between what different ministries are doing and be pandemic ready if, God forbidden, this happens in future. So we have another mission which is in the pipeline called National Livelihood Mission. Again, how do we connect science and technology to really the grassroots level? So this also will cover the fisherman community, how the science and technology interventions can be taken to those who are at the other end, which are not getting benefited so much, and how we can take S&T solution to them. So all these missions, and the last one, last month was discussed, was the carbon capture, utilization and sequestration. And this is again will be launched in coming months. So this was just to give you a feel how Office of PSA looks at what is contemporary, what is required for the country, and see how different ministries and departments really lead this mission, because we are the catalyst and we are not the implementing body. So I thought so much is happening in Ministry of Earth Sciences. So I'll just take a little 5 minutes maybe on saying how the quantum technologies could be useful in coming future for Ministry of Earth Sciences. I know it is, you all of you will say it's too futuristic, it doesn't worry me, but I request some of you to start thinking about it, so that when the technology is all ready and deployable, in other domains. Ministry of Earth Sciences can also be a useful partner and also make very, very substantial contributions. So this mission is led by DST, and which has other ministries, departments participating, defense, DAE, space. And this mission is looking at quantum communication, quantum computing, sensors, quantum sensors, and metrology. And the fourth one is the quantum devices. So in particular, I thought in the next 5 minutes or 6 minutes, I'll point out why we should be worrying, not worrying, why should we be looking at quantum computing the way you looked at classical computing 50 years back. Classical computing is all mature. You are buying the latest computer as we speak, as was mentioned. Question is, this technology is in the making, and it is good idea to keep track of it and see how can you be the beneficiary of the tremendous possibilities of quantum computing. In that connection, I just refer to one recent paper. This is a very interesting review written more or less like a layman, for a layman, but looking at quantum computers for weather and climate prediction, very much in your arena. But it also says very interestingly a take on the movie, The Good, Bad, and the Ugly. But it says the good, the bad, and the noisy. So I'll tell you why these three attributes are given here. And it looks at what difference can it make when you look at weather and climate prediction using quantum computers. And this is something which people, many groups in the world are doing it. And this is still very much in the research stage. And I think this is also the right time for India to look at that and be in a contemporary mode and not in the catch-up mode. So this is something, the reason for my choosing to talk few minutes on this. So this is something all of you have read in your bachelor degree, that quantum mechanics is something which was the phase one, quantum mechanics 1.0 is right from 1913. All of you know, you have read spectral lines of hydrogen atom cannot be explained without quantum mechanics. You know wave particle duality in 1923. You know Schrodinger equations. You know all the foundations of quantum mechanics almost 100 years back. Now, what we are today, and this revolution gave rise to so many technologies that you don't even realize that is due to quantum mechanics. All your transistors, lasers, whatever the machines you have, sensors, many of them, or most of them, I would call, are based on quantum mechanics. Now, why don't we realize them if it is quantum? The reason is, all of you realize there is gravity. Why? Because when you fall down, or when Newton sees an apple falling, you know there is gravity, and it does not need any equation or a huge insight to explain to a child even that there is gravitational pull, gravitational forces. Quantum mechanics is not like that, because you don't realize that quantum mechanics is working, because really the manifestation of that, if you want to see, they'll be at the subatomic particles, on electrons, at protons, neutrons, photons. All those properties are governed by quantum mechanics. You don't deal with it because this is not affecting you. But the consequence of those quantum mechanical properties is what we have been looking at. Now, what has happened in the last 20 years, there is a realization in the second revolution that you can really control this quantum individual systems. You can control them. You can harness, I'll tell you, two properties of quantum mechanics to your advantage. You can make a a huge quantum leap in your understanding of nature, but not only understanding, but making technologies to contribute to your lifestyle and betterment of society. So this second revolution, interestingly, again, Richard Feynman conjectured in 1982. You can see the futuristic vision. He said, why can't we simulate physics like the hydrogen atom or any system using quantum mechanics, quantum mechanical computers? Why do we have to go to Newman classical computer and waste a lot of energy and solve the quantum problems? So at that time, people thought it's an idea. Probably it is just a hypothetical idea. It will not work. But sure enough, in the last 10 to 12 years, it has become a reality. So I thought, pardon me if I take you to 101 course on quantum mechanics, but only the bare minimum. Don't get scared. Now, in classical computer, you work with bits, 0 or 1. You say something is off or something is on. You can divide anything in two states. The transistor is on, transistor is off. In terms of 0 and 1, you do everything. All your numbers you write in the binary, all your operations, the gates which make the operations on these bits using transistors and whatnot, and your entire life now depends on classical bits. So now from classical bits, one now wants to go to quantum bits. And that simplest way is that you have 0 and 1 bits, but now you do not say my system is 0 or 1. You can, quantum mechanics allows you, this called superposition principle, that it can be anywhere between 0 and 1 simultaneously. This is the spooky physics, which is called in earlier years. This is what the superposition, the one qubit encodes 0 and 1 simultaneously. And how much of 0 and 1? It is given by these amplitudes, which are complex, A and B, the square of them. So now this is the probability. Now, once you have superposition, you cannot talk the state is 0 or 1. You have to immediately say it is 0 and 1. So you can see that once you have that, the second thing which happens in quantum mechanics is the entanglement, which means one qubit by my hand and the other qubit get entangled. This entanglement tells you if anything happens to one qubit, it is immediately known to the other qubit. That is the power of entanglement. This does not happen for classical systems. It happens for quantum systems. So the two principles which you take from today's talk is superposition and entanglement. And that is the one which is all powerful. Why is it all powerful? Now, once you have that, if you have a 2-qubit system, then it will have 4 permutations which are immediately there simultaneously. For 2 qubits, you have 4 simultaneous positions. For 3 qubits, it is 8. 4 qubits, you can see 16. So you increase by a factor of 2. All this is simultaneously present in your qubits. If you have a 4 qubit, 16 numbers can be stored or can be codified in the 4 qubit. Imagine if you had 50 qubit, only 50 qubit. Can you read these numbers? All these possibilities exist to store in 50 qubit quantum computer. But when you check the state of the computer, because you have to know after the operation what is the qubit, and that itself is only 50 because the measurement itself does something. So this is the beautiful quantum mechanics which tells you that even if you have 50 qubit machine, you can have so many numbers stored or addressed at the same time. Now this has immediate implication, which I will come to in a minute. But this you have to realize that this is something, entanglement is very critical here. Now, this entanglement is fragile because the atmosphere, the room temperature, they will try to spoil this entanglement. So that is your enemy. So you need to do something special to preserve this quantum qubits and entanglement and superposition. And that's where the technology is. Now, there are many, many possibilities now. Good news is 464 qubit machine is available for commercial use on the cloud, or 434. 1000 qubit machine is going to be there anytime by 4 vendors. So this the progress in this has been phenomenal, which was all theoretical, has now come to a actual calculation, actual computation. And these are the various physical qubits. I will not go into superconducting junctions, semiconducting junction, trapped ions, whatnot, photonics. All these are still being worked upon. But what has made headway is the Josephson junction, superconducting qubits, that is in the market. And the neutral atom and trapped ion atoms are also now in the commercial domain. So this is the what has happened in the last 10 years as we speak. And every day there is a progress. So you are living in an era which is 1912 transported to 2024. On a daily basis now, the technology is enhancing. And that's why it is so exciting. So this one slide on why should you worry about it. Actually, it is a problem of national security right now. The reason is that all your communication, which you are doing on your mobile, bank transfer, everything is based on some classical cryptology, right? That's how you get a message when you do two end-to-end encrypted. The WhatsApp message will give you. So all this RSA, for example, the traditional supercomputer cryptography, they are based on factorization of a number. Simply, if you have a number 21, immediately a child will say it is 7 into 3. What is so great? But if the number becomes very large, the computers take enormous years. For example, if it is a 128-bit AES cryptology, it will take 100 trillion years to break that code. And I don't think you will live that long, so you're happy. If it is 2048 bit, which is done for extremely sensitive message, if at all, this will take more than the age of the universe to crack that code with your classical computers. Please remember. But if you have a quantum computer, if of 4000 qubit, right now we are at 1000 qubit, and you can have 100 million gates on quantum computer, then it will only take 10 seconds. So from age of the universe to 10 seconds is the power of quantum computers. You can see it is extraordinarily scary because all your transactions, if there is a quantum computer available, it need not be with you or it need not be in your room. Anyone can break that code if the quantum computers become available, even with 128-bit classical encryption. And that's the worry, that once that happens, then nothing is safe. So actually, in many, many countries, there are now national missions and national warnings on how to become quantum safe. So that's what is called post-quantum cryptography, that even if quantum computers become available, your code will be safe. That's what is happening, or the quantum key distribution using quantum mechanics. So all that is the requirement once the quantum computers become easily available. What people are doing now, and I am told, people now store the information and analyze it when the quantum computers become available. So store now, analyze later. That is also a strategy many adversaries are taking, because that will tell them what exactly code you were using at that time. So this is a very, very important thing for any country to look at. This is something, oh, I lost track of time. Another 10. You have all the time in the world, right? Because you deal with Earth's time. So on Earth's time scale, this is nothing. Okay. No, I'll just take 10 minutes, maybe 15 minutes. So this is what is called quantum supremacy. This you might have heard the word in popular press. The idea is do problem on quantum computer, which you cannot do on classical computer. That's the quantum supremacy. And there have been a huge race, national competitions on who will achieve quantum supremacy. Now, this is what I quote, quantum supremacy was coined by John Preskill from US. And this is what everyone is trying to do. So what are the problems you can look at? For example, you know that photosynthesis is the best energy harvesting because the efficiency is close to 100%. But nobody knows in this cycle, which I have written on this, what are the mechanisms or what are the processes which are taking place. You know it's happening, but you do not know the actual chemistry and physics of it. Which quantum states are participating, which ones are getting modified. Why do you want it? Because if you know that, you can mimic that in your laboratory and have wonderful photosynthesis, photovoltaic cells, anything, drug molecular discovery. The drug discovery is all based on understanding how the drug interacts with a protein or with any other organism. This is what is now is the progress which people want to look forward. Look at the problems which cannot be done by classical computers. But the trouble right now, as we speak, 2 years back, which has improved, is the noise or the decoherence in the quantum bits. So after 100 or 300 gates, the noise increases. That noise actually starts killing because quantum mechanics is based on probabilities, I told you. So you cannot have too many errors. You can afford some errors. Right now, people want to minimize the error. So you will again hear a word, how many errors are allowed in your quantum computers? One will say 1 in 10,000, 1 is 20,000. But if you want to break the code, which I mentioned, you need much less error possibility. And this is what the progress is being made. So I just thought I'll close this discussion by mentioning very interesting things. Supposing you have a numerical weather prediction model, supposing, which you already have, and you have 1 billion variables because you want to have the right grid, right time on which you want to predict, or many more things. 1 billion, I think, is a reasonable number. And the classical computers, I don't know at what is the limit of that. But let's say this is the one. If you have that, then you will only need 30 qubit quantum computer. Only 30. And I told you 440 qubit machine is available commercially now. So this is a possibility. But is that all? No. Because next question will be, how will you encode nonlinear dynamical equations, for example, Navier-Stokes equation of a numerical weather prediction model into something which is called unitary transformations in quantum mechanics, that a state can evolve. So because you have the variables, you have the initial condition, as Dr. Ravichandran keeps on saying, the actual thing is what is your initial condition on which states will evolve. Once you have that, if you have the initial condition, then this unitary transformations in quantum computers will evolve it. And then in the end, you will measure what is the state of the qubits or those your variables. This is actually in principle what has to be done by a quantum computer. Question is it happening? So again, I'll tell you in a very summary what is the status. There are 3 possibilities now you can do. One, you have a quantum computer, which I told you, dealing with the various physical qubits. So these quantum computers, they consist of unitary evolution of quantum states followed by measurements of the qubits. Sorry for being technical, but I thought at least in their entire universe, you will have few guys who will understand. So I don't want to dilute quantum mechanics too much because people will kill me. Feynman will come down on earth and kill me. So I don't want to be too vague. But these are very, if you have done quantum mechanics earlier, it will connect with some way. So you need a controlled unitary evolution. Second possibility, which is already there in a big way, is these are the machines available. These are called quantum annealers. There is a one company called D-Wave machine. It's commercially available. I think India is trying to get one in some lab. I forget the place. So what does this quantum annealers do? They're slightly different from quantum computers. They will seek to encode the computational task as a minimization problem of a target function. In your weather prediction, you have a target function. It will try to minimize. That's your goal in life. Now, what does it do? By carefully tailoring the interaction between the qubits, the solution of the minimization is given by the lowest energy state of the machine. So this is much less demanding than quantum computers. Question is, all problems, can they be cast in this form? Whether your nonlinear weather prediction model can be cast in that. There are some papers which I was just looking at. There is a possibility, but experts have to see. I am not an expert. Third one, which is more attractive, that you combine your HPC with the quantum computers. So you are already having HPC in your ministries. You are buying another one. Can the two combined together can give you much more result? Why? Because what you can do is that quantum hardware will be used to evaluate a parameterized target function. That's what you want to do in your weather model. The overall task is to find the parameters which minimize the target function. Now, after each evaluation of the target function on a quantum computer, the classical computer will determine new set of parameters for which the target function will be evaluated. So it's a combination of the two, and that is going to be possible sooner than later. So my suggestion is to see how this hybrid mode can really amplify your capabilities in weather prediction. So I think I will not say more, and I'll just take another few minutes to talk on another thing, what is called earthquakes. Again, enormous work your ministry is doing, and there is no scientific technique available to predict the occurrence of earthquakes with reasonable degree of accuracy with regard to space, time, and magnitude. That's the challenge, scientific and technological challenge, and still there are no solutions. So what you want to do is the P wave arrival time and see how much leeway you can give. Is it 3 minutes, 5 minutes, 7 minutes before the earthquake hits another place? And this is what is done. And it's a wonderful effort all over the world. It's happening. Question is, what can you do on a research level where it can help in the science of earthquakes? So many people are looking at laboratory experiments to generate earthquake-like phenomena and learn from them. It's not to replace the earthquake study, but to learn from the earthquake simulation, not on a computer, but on a physical system. But the output of the physical system looks somewhat like earthquakes or more like earthquakes. So I'll tell you one toy experiment which we did few years back. So when Ravi asked me to give this talk, suddenly it occurred to me that I have thought about earthquakes a few years back when I was in my other avatar. And why not I just put it for your amusement? You will see how easily you can generate earthquake-like statistics. Question is, what do we do with it is what you have to see. So I'll just tell you a very simple experiment. So this is the paper we published in Nature Communication, which had enormous press coverage and so on. So quantitative earthquake-like statistical properties of the flow of soft materials below yield stress. So there are keywords which you may not recognize, but what is a soft material? Now, soft material, this work was done with my graduate student and this graduate student and two collaborators who are actually earthquake experts. They work on complex system. So when Didier Sornet was visiting ISC and giving a named lecture, he was talking about earthquakes. How do we use earthquake data to learn more? And he showed some data, which I'll show you, which looked somewhat like we were observing in our other experiments. So after that lecture, I started talking to him and we resulted in this. So it's a learning I did from a earthquake expert and saw what we could learn. So this is something. Now, many things are in earthquakes. I will not go. You are all experts. And the point is how we can mimic the earthquakes which occur, for example, in the tectonic earthquakes, but you can have also volcanic induced earthquakes and so on. And aftershocks, you have stick slip behavior, all that. How do you do? This is the data which is shown. This is the data from Kobe earthquake, Japan, 1995. So this is what your ground acceleration and versus time. And this is where the earthquake occurs. This is the before earthquake. This is the after earthquake. And this noisy data, what does it have? So there are 3 or 4 laws which we learned in earthquakes. One is the Omari law, which you all know, that what is the frequency of quakes after the major shock. How many shocks will occur as a function of time? This is a power law. It decreases as a function of power law, and alpha is close to 1. So the number of aftershocks will decrease with time as 1 over time. That's what this power law says. And this has been observed for many earthquakes. And for example, in this data from another earthquake, this Omari law or the modified Omari law is fitted, and you get an exponent which is 1. So this is well known in earthquake domain. Other one, which is again known, what is the earthquake frequency which occurs in a given region? What is the probability? So this is what you call as Gutenberg-Richter law. This is again, if you know the energy of the earthquake or the intensity of the earthquake, it is a power law in that. What it means is, it's again a power law. It means something very physical. What it means is that if you have an earthquake, for example, in UK, you can say that if the earthquake is between 3.7 and 4.6 on a Richter scale, what is the frequency will it occur? This law says it will occur once a year. It's a statistics. But if it is 4.7 to 5.5, it will occur once in 10 years because UK is not earthquake prone. But if it is 5.6 and above, this law predicts it can be variation. There can be extreme events, but majority of it will obey this. It says it will occur once in 100 years. So far, earthquake occurrence has been seen to follow Gutenberg-Richter law. Is that correct? There may be experts in the hall, but this is what I understand from the literature, that Gutenberg-Richter law is very well obeyed with almost 95% accuracy. So this is what, and the second and the other one, sorry, I will, is what is the frequency with between the two quakes in that, and that is again a power law. Again, I will not say. This is called interoccurrence of earthquakes. I have taken more time, but 5 minutes. Now, what is a soft matter? This is the soft matter which you deal with daily life, whether it is a sauce, whether it is a shampoo, whether it is a paint, whether it is the coffee in a machine, whether it is colloidal particles, milk, all are examples of what is called a soft matter, or your toothpaste. I will not give you a whole description of them. These are neither liquid nor solid, because you can take a toothpaste and put it on your brush. It does not flow like water, but it's not a solid also. So it is in between. This is called soft matter. Now, if you take this soft matter and try to see when it flows, this is the shear rate versus the shear stress. Below a certain value, it will not flow. That's exactly what you see in toothpaste. But above that, it will flow. So this is what is known, some law which I have written. And if it was Newtonian like water or honey, it will just simply have a linear relation. Sigma is equal to eta gamma dot, your high school Newton's law. This is what we will be dealing with. Now, so the experiment, I will not describe what it is. We have certain material called a soap molecule. You put them in water, they form polymers, polymer-like system, cylinders. These cylinders, they can align, and which we call nematic phase for argument. Now, when you put them in water, they will have domains of this aligned things. So these are same material, but aligned differently. So you have you are simulating Earth like a polycrystalline, the tectonics we want to call it. They are one what you are created. We put them between the two plates and shear this. If it was normal material, nothing will happen below yield stress because there is no flow, nothing will happen. For this material, something very exciting happens. Above yield stress, it will flow, whatever is known. But we were interested in this regime where we apply very, very small stress, very small stress, much below yield stress, and material starts behaving very interestingly. Let me show you. This is one experiment as we are collecting the data. Stress is fixed much below the yield stress. Nothing should have happened. But now you can see that as a function of time in seconds, it has huge bursts and then it becomes very silent, which is what is expected in this. Now we were surprised what it is happening. So this, let me just spend time on it. This is the data. Oh, after this, nothing happens. Material is very calm, like after the earthquake. But this one and this data, if you look together, if I expand, you cannot distinguish. Actually, if I show to a earthquake person, and that is what I showed to Didier Sornet, he couldn't make out that it's not a earthquake data. So this is what intrigued us, and we did the usual statistical analysis. So this can happen as a function of many parameters. I will not give on detail. And it can also happen in another material, for example, where there can have multiple earthquakes. A, B, C, D, many earthquakes after some time. You can play with it. So you have now a material in your lab where you can mimic the earthquakes for some good reason. I have not yet told you that. So idea was, what can you learn? So what we did all the analysis what earthquake scientists do. What is called Omri law in terms of wavelet transform. I'm sure some of you will be using. You plot the wavelet coefficient. It exactly follows Omri law. Whatever you do. We did Gutenberg-Richter exponent. Absolutely the same exponent as earthquake. Same 1.6 of epsilon raised to power this. Exactly what earthquake data showed. Interquake waiting time, again the same exponent as earthquake. So all 3 or 4 known statistical properties, same exponent we see. Then we asked, what is good for it? What is so great about it? Can we do something more which geophysicists cannot do? So we want to challenge them. You know, it's always a ego boosting. If you can do something which others can't do, you feel happy because it puts a challenge. What we did, we can now image what is happening inside when this earthquake is happening, which I think so far earthquake scientists cannot do, right? Unless they sacrifice themselves, right? They can't do it. So we wanted to know what is happening on the reorganization of this tectonics like domains when earthquake is really happening. And this is what we did with the imaging. I will not go into detail. When this happens, oh, I'm sorry. We could focus at every point and we image them. In the silent one, images were completely static. Nothing was happening. on the in our image. But when we had this earthquake happening, earthquake, we call it actually gel quake. Or my sorry for this word, we called it gel quakes, and referee didn't object, so we said okay, gel quakes is good. So gel quakes, when it's happening, enormous reorganization is happening, and this is what we want to analyze, and this is what we did. We did various analysis. I will not go into detail. We calculated computational information density. We calculate Fourier transform of that to get you the length scale. And after the earthquake, it is all very quiet. So the domains are coming together. They are moving against each other by a very small stress which is applied, much below yield stress, and they reorganize. I think this I will leave. Beauty is if you scale the events, they are exactly this thing, because tectonics happen on the 100-kilometer length scale. Our length scale is 10 micron. So we have a length scaling by 10 to the power 10. And the time duration of earthquake clusters to year is 10 to the power 8 second. Ours is 1000 second. Again, we have a time scale. If you take these two things, all the parameters get scaled, whatever people have observed in the earthquake, to our data. So it's a complete correspondence quantitatively. So that is something we have to look at. So this is a summary. I will not go into what can we learn. Can we use AI tools to look at this? That is what the DDS Sornet was interested. And this is something many other things can be done. But I think I have taken a lot of your time. This is another area which fascinates me. AI and robotics, again, a huge field in your earth sciences. And this is again where India should be making a mark in coming years. So I will not spend time. And thank you once again for this opportunity to really discuss this. And I hope it